The number is so absurd that when physicists first calculated it, many assumed they had made a mistake. They checked their arithmetic, they revisited their assumptions, they ran the equations again and again and again. The answer never changed. According to the most successful theory in the history of physics, empty space should contain so much energy that a single cubic centimetre of vacuum would outweigh the entire observable universe. Not by a factor of 10, not by a factor of 1,000,000, by a factor so large that writing it out would require 122 zeros. This is the vacuum catastrophe. It represents the single largest disagreement between theoretical prediction and experimental measurement ever recorded in the annals of science, larger than any error in astronomy, chemistry, biology, or any other physics calculation in history. For more than 50 years, some of the most brilliant minds on Earth have tried to resolve it. Every attempt has failed. The number sits there, mocking us, a monument to the limits of human understanding, or perhaps a doorway to something we have not yet learned to see. To understand how we arrived at this impossible discrepancy, we must begin not with what we don't know, but with what we thought we knew absolutely. We must begin with the nature of nothing itself. Imagine, for a moment, that you could remove everything from a region of space. Every atom, every photon, every particle of dust and wisp of radiation. You pump out all the air. You shield the region from light. You cool it to temperatures so close to absolute zero that even the faintest thermal vibrations cease. What remains? For centuries, philosophers and scientists assumed the answer was simple. Nothing. A void. An absence so complete it needed no further description. The ancient Greeks called it keinon, the empty. Aristotle denied its very existence, insisting that nature abhors a vacuum. But by the 20th century, physics had seemingly settled the question. The vacuum was simply space without matter, a stage waiting for actors, a canvas before the paint. Then came quantum mechanics, and everything changed. The story begins in the early 1900s, in the cramped offices and cluttered laboratories of Europe, where a handful of physicists were dismantling the clockwork universe their predecessors had so carefully constructed. Max Planck, a conservative German theorist who once advised a young student to avoid physics because all the major discoveries had already been made, accidentally ignited a revolution. Studying the glow of heated objects, he found that the only way to explain the data was to assume that energy came in discrete packets, quanta, rather than flowing continuously like water from a tap. Planck himself was uncomfortable with this conclusion. He spent years trying to find a classical explanation. He never did. The quantum had arrived, and it would not be dismissed. Over the following decades, the implications cascaded. Einstein showed that light itself was quantized into particles we now call photons. Bohr revealed that electrons in atoms could only occupy certain discrete energy levels. Heisenberg formulated his uncertainty principle, demonstrating that you could never simultaneously know both the exact position and exact momentum of a particle. The more precisely you measured one, the more uncertain the other became. This was not a limitation of our instruments, it was a fundamental feature of reality. But perhaps the strangest consequence of all lay hidden in that uncertainty principle, waiting to be discovered. If you could never know precisely the position and momentum of a particle at the same time, what happened when you tried to describe a region of space with no particles in it at all? The answer, when it came, was deeply unsettling. You could not have exactly zero particles with exactly zero energy in any region of space. That would violate the uncertainty principle. The very concept of a perfect vacuum, empty, still, silent, was quantum mechanically forbidden. Instead, the vacuum seethed. Picture a calm ocean on a windless day. From a distance, the surface appears flat, still, glassy. But look closer. Lean down until your eyes are inches from the water. You will see countless tiny ripples, fluctuations, disturbances too small to notice from afar, but never truly absent. The water is never perfectly still. It cannot be. Thermal energy keeps its molecules in constant random motion. Even if you could cool it to near absolute zero, quantum effects would maintain a residual trembling, the water's zero-point motion. Now imagine that this ocean is not made of water, but of fields, quantum fields to be precise. fields that permeate all of space, that underlie every particle in the universe. The electromagnetic field, which gives rise to photons, the electron field, which gives rise to electrons, the quark fields, the neutrino fields, the gluon fields. Every type of fundamental particle corresponds to its own quantum field, extending throughout the cosmos like invisible oceans layered on top of one another. In quantum field theory, particles are not tiny billiard balls. They are excitations, ripples in these underlying fields. A photon is a ripple in the electromagnetic field. An electron is a ripple in the electron field. When we say a region of space contains no particles, what we really mean is that no large, stable ripples are present. But the small ripples, the quantum fluctuations, can never be eliminated. They are sewn into the fabric of reality by the uncertainty principle itself. This is zero-point energy, the irreducible minimum energy that quantum fields must possess even in their ground state, even in the absence of any particles, even in the coldest and emptiest regions of the universe. For a single quantum field, the zero-point energy is already enormous. But there is not just one field. There are many, at least 17 according to the standard model of particle physics, and possibly more. Each field contributes its own zero-point energy. Add them all together, and you get the total vacuum energy, the energy of empty space itself. When physicists first performed this calculation in the mid-20th century, they expected the answer to be small. They assumed that the various contributions would largely cancel out, leaving a residual energy close to zero. Nature, they believed, would be elegant. Nature, they believed, would behave. Nature did not behave. The calculation proceeds as follows, and even a simplified version reveals the staggering scale of the problem. Consider a single quantum field, say the electromagnetic field. In its ground state, this field experiences quantum fluctuations at every point in space. These fluctuations can be thought of as virtual photons, flickering in and out of existence too quickly to be directly observed but contributing to the field's total energy. To calculate the zero-point energy, you must sum the contributions from fluctuations at all possible wavelengths. Short wavelengths correspond to high frequencies and high energies. Long wavelengths correspond to low frequencies and low energies. The sum runs from the longest wavelengths you can imagine down to the shortest. But how short? In principle, you might think there is no limit. You could consider fluctuations with infinitely short wavelengths and infinitely high energies. If you do this, the sum diverges. The calculated energy becomes infinite. This is clearly unphysical. The universe does not contain infinite energy, so physicists introduce a cutoff. They assume that physics as we know it breaks down at some very short distance scale, and fluctuations shorter than that scale should not be included. The natural choice for this cutoff is the Planck length, approximately 1.6 times 10 to the negative 35 meters. This is the scale at which quantum effects and gravitational effects are expected to become equally important. Below the Planck length, our current theories, both quantum field theory and general relativity, are likely to fail, replaced by some as yet unknown theory of quantum gravity. When you perform the calculation with the Planck cutoff, you get a finite answer. But that answer is mind-bendingly large. The vacuum energy density works out to roughly 10 to the 93 grams per cubic centimeter. To put this in perspective, the density of an atomic nucleus, the densest ordinary matter in the universe, is about 10 to the 14 grams per cubic centimeter. The theoretical vacuum energy is 79 orders of magnitude higher. This is already disturbing. But the true catastrophe comes when you compare this prediction to what astronomers actually observe. The energy of empty space, if it exists, should have observable consequences. According to Einstein's general theory of relativity, energy, any energy, curves spacetime. Mass curves spacetime, which is why the Earth orbits the Sun. But so does energy that has nothing to do with mass. If the vacuum possesses energy, that energy should curve spacetime too. The effect of vacuum energy on the large-scale structure of the universe is captured by a single parameter in Einstein's equations, the cosmological constant, traditionally denoted by the Greek letter lambda. A positive cosmological constant acts like a repulsive force, pushing space apart and causing the expansion of the universe to accelerate. A negative cosmological constant would do the opposite, pulling space together and eventually causing the universe to collapse. For most of the 20th century, cosmologists assumed that the cosmological constant was exactly zero. There seemed to be no evidence for it. An exact cancellation was aesthetically appealing. The universe appeared to be expanding, yes, but at a rate that was slowing down over time as gravity tugged on galaxies and tried to pull them back together. Everything seemed consistent with a vacuum that contained no energy at all. Then, in 1998, two independent teams of astronomers made a discovery that shattered this assumption. The teams were studying Type Ia supernovae, stellar explosions so bright that they can be seen across billions of light years. These supernovae serve as standard candles, objects of known intrinsic brightness that allow astronomers to measure cosmic distances with high precision. By comparing the apparent brightness of distant supernovae to their known luminosity, and measuring their redshift to determine how fast they are receding, the astronomers could chart the expansion history of the universe. What they found made no sense. The distant supernovae were dimmer than expected. They were farther away than they should have been if the expansion of the universe had been steadily slowing. The data pointed to an astonishing conclusion. The expansion was not slowing down. It was speeding up. The universe was accelerating. This acceleration required an explanation, and the simplest one was a cosmological constant, a non-zero vacuum energy that pushed space apart. The supernova data allowed astronomers to estimate the magnitude of this energy. The answer was extraordinarily small, roughly 6 times 10 to the negative 30 grams per cubic centimetre, expressed as an equivalent mass density, tiny, almost imperceptible. But compare this to the theoretical prediction from quantum field theory. The theory predicted 10 to the 93. The observation revealed 10 to the negative 30. The ratio between them is 10 to the 122, 1 followed by 122 zeros. This is the vacuum catastrophe. This is the largest discrepancy between theory and observation in the history of physics, in the history of science. Nothing else comes close. Even the most spectacularly wrong predictions in other fields pale beside it. It is not a factor of 2, or 10, or 1,000,000. It is a number so vast that if you tried to write out all the zeros, you would need more than 2 lines of text just to fit them on a page. How could the most successful theory in physics be so catastrophically wrong? The first response, of course, was to look for a mistake. Surely something had gone wrong in the calculation. Perhaps the cutoff was chosen incorrectly. Perhaps some contributions had been double counted. Perhaps the whole framework was being misapplied. Physicists spent years exploring these possibilities. They found errors, yes, but nothing that came close to resolving the discrepancy. You could lower the cutoff from the Planck scale to the scale of electroweak symmetry breaking, a difference of 17 orders of magnitude, and the prediction would still be off by over 100 orders of magnitude. You could introduce new particles or new symmetries, and while some cancellations might occur, they never cancelled enough. One of the most popular proposed solutions was supersymmetry, a theoretical framework that posits a deep symmetry between bosons, particles like photons and gluons, which transmit forces, and fermions, particles like electrons and quarks, which make up matter. In a perfectly supersymmetric universe, the zero-point energy contributions from bosons and fermions would exactly cancel, leaving the vacuum energy at 0. For a while, this seemed promising. Supersymmetry was theoretically elegant. It solved other problems in particle physics. It predicted new particles that colliders might soon discover. But there was a catch. Supersymmetry, if it exists, must be broken in our universe. We do not observe superpartners, the supersymmetric twins of known particles, at the energies we can probe. This means that even if supersymmetry were true, the cancellation would not be perfect. There would still be a residual vacuum energy, reduced but not eliminated. Calculations showed that this residual energy would still be tens of orders of magnitude too large. No known mechanism could reduce the discrepancy to acceptable levels. The catastrophe remained. By the 1980s, the vacuum catastrophe had matured from a curious puzzle into an existential crisis for theoretical physics. The most celebrated framework for understanding the fundamental forces of nature, quantum field theory, validated by countless experiments to astonishing precision, made a prediction about the most basic property of empty space that was wrong by a factor beyond human comprehension. Some physicists began to wonder if the problem lay not in the calculation itself, but in the question being asked. Perhaps there was no reason in principle to expect the vacuum energy to be small. Perhaps we simply happened to live in a universe where it was small, and the explanation for why was not dynamical, not derived from fundamental equations, but anthropic. The anthropic principle, in its various formulations, suggests that we should not be surprised to find ourselves in a universe compatible with our existence. If the vacuum energy were much larger than what we observe, galaxies would not have formed, stars would not have ignited, and we would not be here to ask the question. The observed smallness of the vacuum energy might not require a physical explanation. It might simply be a selection effect. We observe a small vacuum energy because only universes with small vacuum energy produce observers. This line of reasoning was controversial from the start. Many physicists found it distasteful, even dangerous. It seemed to abandon the quest for understanding, to replace explanation with coincidence. If you could always invoke the anthropic principle when calculations failed, what was the point of doing physics at all? And yet, as the decades passed and no dynamical solution emerged, the anthropic approach began to gain traction. Its most influential advocate was Steven Weinberg, the Nobel laureate who had helped construct the Standard Model itself. In 1987, Weinberg published a paper that would reshape the debate. He asked a deceptively simple question: how large could the cosmological constant be while still allowing galaxies to form? The logic was straightforward. If the vacuum energy is positive and too large, it will cause space to expand so rapidly that matter never has a chance to clump together. Gravitational attraction, which pulls matter into clouds and then into galaxies, would be overwhelmed by the repulsive effect of the cosmological constant. No clumping, no galaxies, no stars, no planets, no observers. Weinberg calculated the threshold. He found that the cosmological constant could be at most about 100 times larger than the matter density of the universe at the epoch of galaxy formation. Any bigger, and structure formation would be suppressed. Observers would not arise. This was a striking result. The observed cosmological constant, measured a decade later, fell comfortably within Weinberg's anthropic bound. It was small enough to allow galaxies to form, but not dramatically smaller. It was roughly the largest value compatible with our existence. To some, this was evidence that the anthropic approach was on the right track. The vacuum energy was not zero, as exact cancellation would predict, nor was it 10 to the 93, as naive quantum field theory suggested. It was instead precisely in the narrow range where observers could exist. This seemed too coincidental to be an accident, but the anthropic explanation raised as many questions as it answered. If the vacuum energy in our universe was set by selection effects rather than fundamental physics, then there must be other universes with different vacuum energies. A vast ensemble of universes, a multiverse, in which the cosmological constant varied from place to place, with observers only arising in the rare regions where conditions were hospitable. This was a radical proposal. It implied that our universe was not unique, that the laws of physics might vary across a cosmic landscape, and that the deepest properties of our reality were ultimately contingent, accidents of location rather than necessities of logic. Not everyone was convinced. Many physicists remained committed to finding a dynamical explanation, a mechanism that would naturally drive the vacuum energy to its observed tiny value. The search continued. It continues still. The years since Weinberg's paper have seen an extraordinary expansion in our observational knowledge of the universe. The cosmic microwave background, the afterglow of the Big Bang, has been mapped with exquisite precision. Millions of galaxies have been catalogued, their positions and motions charted across billions of light years. The expansion history of the universe has been measured to unprecedented accuracy. Through it all, the basic picture has remained stable. The universe is accelerating. The cosmological constant, or something very much like it, is real, but questions have lingered. Is the vacuum energy truly constant, unchanging across cosmic time? Or might it evolve, varying subtly as the universe expands? This distinction matters. A truly constant vacuum energy is the simplest explanation for cosmic acceleration, but it is also the most mysterious. It requires an exquisite fine-tuning that no one can explain. A dynamical form of dark energy, sometimes called quintessence, might be more natural, arising from a slowly rolling scalar field or some other new physics. Detecting any variation in dark energy would be a revolutionary discovery, pointing toward new physics beyond the standard model and perhaps offering clues to the vacuum catastrophe itself. For decades, observational constraints on dark energy evolution were consistent with a pure cosmological constant. The data permitted small variations, but none were required. The universe seemed content with the simplest possibility. Then came DESI. The Dark Energy Spectroscopic Instrument is a marvel of modern engineering. Mounted on the 4-meter Mail telescope at Kitt Peak in Arizona, it uses 5,000 robotic fiber positioners to capture spectra from thousands of galaxies simultaneously. Its goal is to construct the most detailed 3-dimensional map of the universe ever made, charting the positions of tens of millions of galaxies and quasars across 11 billion years of cosmic history. By measuring how galaxies cluster at different epochs, DESI can trace the expansion history of the universe with extraordinary precision. It can detect the subtle gravitational effects of dark energy and test whether that energy is truly constant or evolving over time. In early 2024, the DESI collaboration released its first major cosmological results. The findings were intriguing and unsettling. When the DESI data was combined with other observations, including measurements of the cosmic microwave background and supernova distances, a curious pattern emerged. The expansion history of the universe, as reconstructed from the data, showed hints that dark energy might not be constant after all. The equation of state, a parameter describing the relationship between dark energy's pressure and density, appeared to deviate from the value expected for a pure cosmological constant. The deviation was not dramatic. It was not a smoking gun. Statistical uncertainties were still large enough that the constant cosmological constant remained within the realm of possibility. But the best fit model, the model that described the data most accurately, was one in which dark energy was stronger in the recent past and weaker today. One in which the vacuum energy was changing. If confirmed, this would be profound. A constant vacuum energy poses a fine-tuning problem that no one can solve. But a dynamical vacuum energy, one that evolves with time, poses problems of its own. Why would it evolve in the particular way suggested by the data? What new physics underlies this evolution, and what does it tell us about the vacuum catastrophe that started this entire investigation? The DESI results are preliminary. More data is being collected. Other experiments are underway. The coming years will bring sharper constraints and clearer answers. But for now, the possibility hangs in the air. Perhaps the cosmological constant is not constant after all. Perhaps the vacuum itself is changing. Perhaps the catastrophe is even stranger than we thought. Return for a moment to that empty room, the one you imagined at the beginning. No particles, no radiation, just space itself, cold and silent and still. Except it is not still. It was never still. The quantum fields seethe and shimmer with fluctuations beyond the reach of any thermometer, any detector, any instrument yet devised. Virtual particles flicker in and out of existence, borrowing energy from the uncertainty principle and returning it an instant later. The vacuum hums with a restless, irreducible energy, an energy so vast, according to our best theories, that it should have torn the cosmos apart the instant it was born. And yet, here we are. Here the stars burn, here the galaxies wheel. Here life has arisen, looked up at the sky, and wondered why. For 50 years, physicists have sought an answer. They have proposed new symmetries, new particles, new dimensions of space. They have invoked strings and loops, landscapes and multiverses. They have argued passionately about whether the question even has a meaningful answer, or whether our existence in a particular corner of a vast cosmic ensemble is explanation enough. None of these approaches has solved the problem. None has explained why the vacuum energy is not 10 to the 93, or why it is not exactly 0, but instead sits at the peculiar value we observe. Tiny, but not quite nothing. The catastrophe endures. The number mocks us still. Perhaps the answer lies buried in mathematics we have not yet discovered. Perhaps it awaits a revolution as profound as the one that shook physics in the early 20th century, when the certainties of the classical world gave way to the strangeness of the quantum. Perhaps a young physicist somewhere, working late in a cramped office, is at this very moment scribbling equations that will one day dissolve the paradox and leave us wondering how we ever missed the truth. Or perhaps the vacuum catastrophe is not a puzzle to be solved but a message to be decoded. A sign that our deepest theories, for all their predictive power, are missing something fundamental about the nature of reality. That the vacuum is trying to tell us something we have not yet learned to hear. The story is far from over. The story is far from over. And so we must go deeper. Deeper into the mathematics that gave birth to this paradox. Deeper into the quantum realm where certainty dissolves and probability reigns. Because to truly understand why the vacuum catastrophe persists, why it has resisted every assault for half a century, we must first understand what physicists mean when they speak of the energy of empty space. We must trace the idea back to its origins, to the moment when the quantum revolution revealed that nothingness itself carries a price. The year is 1900. In Berlin, Max Planck sits before a coal fire wrestling with a problem that has haunted physicists for decades. The problem concerns the way hot objects glow. Heat a piece of iron, and it begins to emit light, first a dull red, then orange, then white as the temperature climbs. Classical physics, the physics of Newton and Maxwell, made clear predictions about the spectrum of this radiation, and those predictions were disastrously wrong. According to classical theory, the energy radiated by a hot object should increase without limit as you move towards shorter and shorter wavelengths. A glowing poker should emit infinite energy in the ultraviolet. This was the ultraviolet catastrophe, and it was absurd. Hot pokers do not vaporize everything around them. The universe has not been consumed by infinite radiation. Something was wrong with classical physics. Planck found the answer, though he did not fully understand what he had done. He proposed, almost as a mathematical trick, that energy could not be emitted continuously, but must come in discrete packets, quanta, whose size depended on the frequency of the radiation. A tiny adjustment to the equations, a strange new constant with the symbol h. But this tiny adjustment changed everything. It tamed the ultraviolet catastrophe. It gave the right answer for the spectrum of blackbody radiation. And it opened a door onto a new physics that would take another quarter century to fully walk through. In the years that followed, Einstein showed that light itself came in quanta, particles we now call photons. Bohr applied quantum ideas to the structure of atoms, explaining why electrons orbit only at certain discrete distances from the nucleus. Heisenberg and Schrödinger, working independently, developed the full mathematical machinery of quantum mechanics, a theory that replaced the smooth, deterministic trajectories of classical physics with probability waves, uncertainty relations, and a fundamental fuzziness at the heart of nature. And then came quantum field theory. Imagine you want to describe not just a single particle, an electron say, but the entire electromagnetic field permeating space. Classical physics treats this field as a smooth, continuous entity, like the surface of a calm pond. But quantum mechanics revealed that even fields must be quantized. The electromagnetic field is not a smooth continuum, but a seething collection of photons, each one a quantum of the field. To describe this properly, physicists developed quantum electrodynamics, QED, a theory that married quantum mechanics with special relativity and treated both matter and radiation as excitations of underlying quantum fields. QED was spectacularly successful. It predicted the magnetic moment of the electron to better than 1 part in a billion. It explained the Lamb shift, a tiny discrepancy in the energy levels of hydrogen that classical quantum mechanics could not account for. It became the model for all subsequent quantum field theories, including the theories that describe the strong and weak nuclear forces. The standard model of particle physics, the crowning achievement of 20th century physics, is a quantum field theory through and through. But quantum field theory brought with it a troubling companion, an uninvited guest that refused to leave: the zero-point energy of the vacuum. Consider a simple harmonic oscillator, a mass on a spring bouncing back and forth. In classical physics, you can bring this oscillator to rest. Let it lose all its energy to friction, and it will sit motionless at the bottom of its potential well, perfectly still, with zero energy of motion. But quantum mechanics does not permit this. Heisenberg's uncertainty principle forbids any particle from having a precisely defined position and a precisely defined momentum simultaneously. If the oscillator were perfectly still at the bottom of the well, we would know both its position and its momentum with certainty. This is not allowed. The oscillator must retain some irreducible minimum energy, some quantum jitter that can never be removed, no matter how cold you make it. This is the zero-point energy. Now extend this reasoning to a quantum field. Think of the electromagnetic field filling all of space. At every point, the field can vibrate. It supports oscillations of every possible wavelength, every possible frequency. Each of these oscillations is a quantum harmonic oscillator. Each one has a zero-point energy, and there are infinitely many of them, because you can always consider shorter wavelengths, higher frequencies, oscillations on finer and finer scales all the way down to the Planck length, that incomprehensibly small distance where quantum mechanics and gravity collide. Add them all up. Sum the zero-point energies of every oscillation mode of the electromagnetic field. The answer diverges. It goes to infinity. This was not initially considered a crisis. Physicists in the 1930s and 1940s were accustomed to infinities cropping up in their calculations. They developed techniques, renormalization, to isolate and subtract these infinities, extracting finite physical predictions from the mathematical morass. In the context of particle physics, you care about energy differences, not absolute energies. If the zero-point energy is infinite but constant everywhere, you can simply define your energy scale relative to the vacuum and ignore the infinite background. It does not affect the physics of particles scattering and colliding. But gravity does not work this way. Gravity cares about all energy, including the energy of the vacuum. According to general relativity, energy and mass curve space-time. The vacuum energy contributes to this curvature just as surely as the mass of a star or a planet. If the vacuum has energy, then the vacuum itself gravitates. It shapes the geometry of the universe. This is where Einstein's cosmological constant re-enters the story. In 1917, Einstein introduced this constant, lambda, as a kind of cosmic repulsion to balance gravity and maintain a static universe. When Hubble showed the universe was expanding, Einstein abandoned the term, calling it his greatest blunder. But the cosmological constant is mathematically equivalent to a uniform vacuum energy density permeating all of space. If the vacuum has energy, then lambda is not zero, and if quantum field theory predicts an enormous vacuum energy, then lambda should be enormous too. The first person to take this connection seriously, to sit down and actually calculate what quantum field theory implied for the cosmological constant, was Yakov Zeldovich. A Soviet physicist of legendary range, he made fundamental contributions to nuclear physics, astrophysics, and cosmology. Zeldovich understood that the zero-point energy of quantum fields could not simply be ignored when gravity was in play. In a series of papers in the 1960s and 1970s, he estimated the contribution to the vacuum energy from the known quantum fields. His answers were alarmingly large, not infinite, because he imposed cutoffs at high energies where new physics presumably took over, but still many orders of magnitude larger than anything compatible with the observed universe. Zeldovich hoped that some unknown mechanism might cancel these contributions. Perhaps positive and negative vacuum energies from different fields might balance out. Perhaps supersymmetry, a symmetry relating bosons and fermions, might provide the needed cancellation. Supersymmetry predicts that every known particle has a partner with the opposite spin statistics. If this symmetry were exact, the zero-point energies of bosons and fermions would cancel perfectly, leaving a vacuum energy of precisely zero. This was an elegant solution, and for a while it sustained hope. But supersymmetry, if it exists at all, is broken at low energies. We do not see the supersymmetric partners of electrons and quarks in our experiments. If these particles exist, they must be much heavier than their known counterparts, which means supersymmetry is broken at a scale far above the masses of ordinary particles, and broken supersymmetry does not cancel the vacuum energy. It leaves a residue, smaller than the naive estimate, but still vastly larger than the observed value. Supersymmetry reduces the catastrophe but does not eliminate it. Other symmetries were tried, other mechanisms were proposed. Perhaps the vacuum energy is somehow screened, the way electric fields are screened inside a conductor. Perhaps new fields exist that dynamically adjust themselves to cancel the cosmological constant. Perhaps the vacuum energy evolves over time, rolling slowly down a potential and approaching zero only asymptotically. These ideas were explored with great ingenuity. Papers were written. Conferences were held. But every attempt to explain the small value of the cosmological constant from first principles ended in failure. The mechanisms that worked for one contribution failed for others. The cancellations that seemed natural in one context introduced fine-tuning problems of their own. The cosmological constant became known as the worst fine-tuning problem in physics, and then, in 1987, Steven Weinberg changed the terms of the debate. Weinberg was already one of the most celebrated physicists of his generation. He had shared the Nobel Prize for his work unifying the electromagnetic and weak nuclear forces, one of the great achievements of the Standard Model. He was known for his mathematical rigor, his physical intuition, and his willingness to take controversial positions. In a landmark paper published that year, Weinberg asked a different kind of question. He did not ask why the cosmological constant has the value it does. He asked what value the cosmological constant must have for observers like us to exist. This was an anthropic argument, and many physicists recoiled from it. Anthropic reasoning has a bad reputation in some quarters. It can seem like an excuse for ignorance, a way of avoiding hard problems by appealing to our own existence. But Weinberg's argument was precise and quantitative. He calculated the range of cosmological constant values compatible with the formation of galaxies. Too large a positive cosmological constant, and the universe would have expanded so rapidly that matter could never have clumped together under gravity. No galaxies, no stars, no planets, no life. Too large a negative cosmological constant, and the universe would have recollapsed before any structure could form. The cosmological constant must lie within a narrow band, enormously smaller than the naive quantum field theory estimate, for observers to exist. Weinberg's anthropic bound was a striking result. It predicted, in essence, that the cosmological constant should be roughly at the edge of detectability, not zero, but small enough to permit structure formation and potentially just large enough to be measured by sufficiently precise cosmological observations. This was years before the accelerating universe was discovered. When the supernova measurements came in, when dark energy was announced, the observed value of the cosmological constant sat squarely within Weinberg's anthropic window. He had predicted, in a sense, that the cosmological constant would be small but non-zero, exactly what the data showed. For some physicists, this was a triumph of anthropic reasoning. The multiverse hypothesis, the idea that our universe is one bubble in a vast ensemble of universes, each with different values of fundamental constants, suddenly seemed less fanciful. If the cosmological constant varies randomly from universe to universe, taking on all possible values across an enormous landscape of possibilities, then observers will naturally find themselves in universes where the value permits their existence. The small cosmological constant we observe is not a sign of fine-tuning by some cosmic engineer. It is a selection effect, like the observation that we happen to live on a planet with liquid water. Most of the universe may be devoid of water, but we could not be having this conversation if our planet were a barren rock or a ball of ice. For other physicists, this was a betrayal of the scientific method. Anthropic arguments, they argued, explain nothing. They do not tell us why the cosmological constant has its value. They merely observe that if it had a different value, we would not be here to complain. This is not physics. It is tautology dressed in mathematical clothing. The multiverse hypothesis, moreover, is untestable. If other universes are forever beyond our observational reach, what distinguishes the multiverse from mere speculation? What distinguishes it from theology? The debate continues to this day. It has grown sharper as theoretical efforts to derive the cosmological constant from first principles have continued to fail. String theory, once hoped to provide a unique and calculable prediction for all physical constants, instead revealed a landscape of perhaps 10 to the 500 distinct vacuum states, each with different values of the cosmological constant and other parameters. Far from explaining why our universe has the properties it does, string theory seemed to multiply the possibilities without constraining them. To some, this validated the anthropic approach. The landscape is so vast that our universe is merely one unremarkable patch in an immense ensemble. To others, it signaled that string theory had lost its way, that the theory was so flexible it could explain anything and therefore predicted nothing. And yet the anthropic argument, for all its philosophical controversy, has a kind of scientific power. It makes contact with observation. It predicted, before the fact, that the cosmological constant should be small but non-zero. It explains why we do not find ourselves in a universe with a Planck-scale vacuum energy. Such universes have no observers to find themselves anywhere. This is not nothing. It may not be the kind of explanation physicists hoped for, but it is an explanation nonetheless. Weinberg himself was cautious about his own argument. He did not claim that anthropic reasoning was the final word on the cosmological constant problem. He acknowledged that it would be far more satisfying to find a dynamical mechanism that set the cosmological constant to its observed value. But in the absence of such a mechanism, in the face of 50 years of failure, the anthropic approach at least provided a framework for understanding why the value is what it is. It transformed an inexplicable coincidence into a selection effect. It turned the vacuum catastrophe, if not into a solved problem, then at least into a problem with a possible answer. The anthropic argument also sharpened the question of what we mean by explanation in fundamental physics. For centuries, science has sought to explain the particular by deriving it from the general. The orbit of Mars is explained by Newton's laws. The spectrum of hydrogen is explained by quantum mechanics. The masses of elementary particles, we hope, will someday be explained by a unified theory that contains no adjustable parameters, a theory so constrained that it predicts everything and assumes nothing. The cosmological constant seemed to mock this aspiration. It was a number that could not be derived from anything. It simply was. The anthropic approach offered a different kind of explanation. The cosmological constant takes its value not because any law of nature requires it, but because we are here to measure it. Our existence is the explanation. The theory is not that lambda equals this particular number for some deep mathematical reason, but that lambda varies across a multiverse of possibilities, and we observe the value compatible with our being observers. This is an environmental explanation, not a fundamental one. It is the kind of explanation a fish might give for why water is liquid at the temperature of its pond, not because any law of hydrodynamics requires it, but because fish cannot live in ice or steam. Many physicists find this profoundly unsatisfying. They believe that the cosmological constant has a value for a reason, a calculable, derivable reason that will someday be understood. They point to the history of science, in which apparent coincidences have repeatedly been explained by deeper theories. The fact that the electron and proton have exactly opposite charges, a coincidence that permits the electrical neutrality of atoms, was explained by grand unified theories and the quantization of electric charge. The fact that the universe began in a state of low entropy, a coincidence essential for the arrow of time, may someday be explained by quantum gravity and the physics of the Big Bang. The cosmological constant, they insist, is not different in kind. The answer is out there. We just have not found it yet. But the decades keep passing, the theories keep failing, and the catastrophe remains. Consider the scale of the problem once more. The discrepancy between prediction and observation is 120 orders of magnitude. That is not a small error to be corrected by a better measurement or a more careful calculation. That is a chasm so vast that no adjustment of parameters, no tweak to the existing framework can bridge it. If quantum field theory is even approximately correct, and all evidence suggests that it is, then the vacuum energy should be enormous. Yet it is not. Either our understanding of quantum fields is missing something profound, or gravity works differently than we think, or the universe is far stranger than any theory yet conceived. Some physicists have pursued modifications to gravity itself. Perhaps general relativity breaks down on cosmological scales. Perhaps the gravitational effects of vacuum energy are somehow screened or suppressed by new physics. Theories like massive gravity, theories in extra dimensions, theories with exotic scalar fields have all been proposed. Each one solves some aspect of the problem while creating new difficulties elsewhere. None has gained wide acceptance. The challenge is not merely to propose a mechanism that cancels the vacuum energy, but to do so in a way that is natural, that does not require fine-tuning, and that is consistent with all the other successes of the Standard Model and general relativity. This has proved extraordinarily difficult. Others have questioned whether the vacuum energy really is as large as the naive estimate suggests. Perhaps the cutoff should be placed not at the Planck scale, but at some lower energy where new physics intervenes. Perhaps the sum over quantum fluctuations should be regulated differently. But these adjustments, while they reduce the magnitude of the discrepancy, do not eliminate it. Even conservative estimates, placing the cutoff at the energy scale of electroweak symmetry breaking, yield a vacuum energy tens of orders of magnitude too large. The problem is not sensitive to the precise details of the calculation. It is robust, stubborn, persistent. And then there is the question of why the vacuum energy is not exactly zero. If some mechanism exists that cancels the cosmological constant, why does it not cancel it perfectly? Why leave a tiny residue, just enough to accelerate the cosmic expansion, just enough for us to detect? This is sometimes called the coincidence problem, and it is almost as troubling as the fine-tuning problem itself. The energy density of matter in the universe has been falling steadily as the cosmos expands. The dark energy density, by contrast, remains roughly constant. For most of cosmic history, matter dominated. For most of the future, dark energy will dominate. We happen to live in the narrow window when the two are comparable. Why? Is this a coincidence? Or does it tell us something deep about the nature of dark energy? Some theorists have proposed that dark energy is not a cosmological constant at all, but a dynamical field called quintessence, a field that evolves over time, with an energy density that tracks the matter density for much of cosmic history before eventually coming to dominate. Quintessence models can explain the coincidence problem, or at least make it less severe. But they introduce new questions of their own. What is this field? Why does it have the properties it does? How does it interact with ordinary matter? And does its potential energy emerge from some fundamental theory? Or must we simply postulate it without derivation? The DESI results, those hints of evolving dark energy, have given fresh impetus to quintessence models. If the equation of state of dark energy really is changing, if W is not constant but time-dependent, then a pure cosmological constant is ruled out. The vacuum is not static. Something is driving its evolution. This would be a discovery of the first magnitude, a clue that the vacuum catastrophe is connected to new physics we have not yet identified. But we must be careful. The hints are tantalizing, not definitive. The statistical significance is modest. Systematic uncertainties remain. The universe has a habit of teasing us with suggestive signals that later dissolve into noise. For now, the cosmological constant, static, unchanging, inexplicable, remains consistent with the data. The case for evolution is intriguing but not airtight. In laboratories around the world, experimenters continue their patient work. They measure the cosmic microwave background with ever greater precision, mapping the faint afterglow of the Big Bang to extract the geometry and contents of the universe. They chart the distribution of galaxies across billions of light years, looking for subtle patterns that reveal the expansion history and the growth of structure. They observe distant supernovae, standard candles that probe the acceleration of space. Each measurement sharpens the constraints on dark energy. Each observation brings us closer to knowing whether the vacuum is constant or evolving, whether the catastrophe has an explanation or only an excuse, and somewhere, perhaps, a breakthrough awaits. A new idea that no one has yet conceived. A mathematical structure that unifies quantum mechanics and gravity in a way that makes the vacuum energy calculable, predictable, inevitable. A revolution as profound as the quantum revolution itself, overturning our assumptions and revealing the cosmos in a new light. But that revolution has not come, not yet. For 50 years, the vacuum catastrophe has stood as a monument to our ignorance. The greatest disagreement between theory and observation in the history of science remains unresolved. The empty room is still humming. The paradox endures. The paradox endures, yes. But science does not stand still in the face of paradox. It probes, it tests, it circles back with new instruments and new questions. And so we must now turn our attention to the theoretical frameworks that physicists have constructed in their attempts to tame the vacuum catastrophe, the intellectual edifices raised against this stubborn mystery. These are not idle speculations. They represent decades of concentrated effort by some of the finest minds of the 20th and 21st centuries, and yet, one by one, each approach has encountered its own barriers, its own limitations, its own quiet failures. The first and most natural response to the vacuum catastrophe is denial, or rather, the hope that the problem will simply go away. Perhaps, some physicists reasoned, there is a symmetry we have overlooked. Perhaps the contributions from different quantum fields cancel precisely, leaving behind a vacuum energy of exactly zero. This is not an unreasonable hope. Nature is full of such cancellations. In quantum electrodynamics, the infinite self-energy of the electron is tamed by renormalization, absorbed into the measured mass and charge of the particle. Perhaps something similar happens with the cosmological constant. Perhaps the positive contributions from bosonic fields and the negative contributions from fermionic fields arrange themselves into perfect balance, leaving the vacuum serene and energyless. This hope finds its most elegant expression in supersymmetry. In a supersymmetric universe, every boson has a fermionic partner and every fermion has a bosonic partner. The zero-point energies of these paired particles are equal in magnitude but opposite in sign. They cancel exactly. In a perfectly supersymmetric world, the vacuum energy is zero. Not approximately zero, not nearly zero, but mathematically, rigorously zero. For a time, supersymmetry seemed like the answer. It was beautiful. It was principled. It emerged naturally from attempts to unify the forces of nature, and it solved the vacuum catastrophe in one clean stroke. But the universe is not perfectly supersymmetric. We do not see the superpartners of known particles wandering through our detectors. The electron has no selectron of equal mass. The photon has no photino lurking beside it. If supersymmetry exists at all, it must be broken, hidden at high energies, invisible at the scales we can probe. And when supersymmetry breaks, the cancellation fails. The vacuum energy does not remain zero. It acquires a value proportional to the fourth power of the supersymmetry breaking scale. If supersymmetry breaks at the energies accessible to our particle accelerators, a few trillion electron volts, the domain of the Large Hadron Collider, then the predicted vacuum energy is still some 60 orders of magnitude too large. The problem is diminished but not solved. The catastrophe persists, merely relocated. The situation worsens when we consider the experimental evidence. Decades of searching have produced no sign of superpartners. The LHC has pushed the allowed mass range for these particles higher and higher, into territory where supersymmetry loses much of its theoretical appeal. If the superpartners are too heavy, the symmetry cannot solve the hierarchy problem in particle physics, the puzzle of why the Higgs boson is so light compared to the Planck scale. And if supersymmetry cannot solve the hierarchy problem, its motivation weakens. The theory that once seemed like the inevitable next step beyond the standard model now hangs in limbo, neither confirmed nor entirely ruled out, but certainly less triumphant than its proponents once hoped. So we move on, searching for other mechanisms that might explain the smallness of the cosmological constant. Perhaps the answer lies not in symmetry but in dynamics. Perhaps the vacuum energy is not a fixed quantity but a variable, one that adjusts itself over cosmic time until it reaches its observed value. This is the idea behind relaxation mechanisms, and it has a certain intuitive appeal. After all, many systems in physics tend toward equilibrium. A ball rolls to the bottom of a hill. A gas expands to fill its container. Perhaps the vacuum too seeks some energetically favourable state, and we happen to observe it after it has settled into the configuration we measure. But the details are fiendishly difficult. To construct a working relaxation mechanism, you need a field or a set of fields that couple to the vacuum energy and drive it towards zero, or toward the small positive value we observe. You need this process to occur over cosmological timescales without disrupting the successful predictions of standard cosmology. You need the endpoint to be stable, or at least long-lived compared to the age of the universe. And you need all of this to happen naturally, without fine-tuning the parameters of your theory to achieve the desired result. Several proposals have been put forward. Some invoke scalar fields with carefully crafted potentials. Others appeal to modifications of gravity, theories in which general relativity is extended or altered to include new terms that absorb or neutralize the vacuum energy. Still, others suggest that the cosmological constant is screened by some mechanism analogous to the Debye screening of electric charges in a plasma. Each of these approaches has its merits. Each has generated papers, conferences, doctoral theses, but none has produced a fully satisfactory solution. The models are often complex, the assumptions numerous, the predictions difficult to test. And the fundamental question remains, why should nature choose this particular mechanism? Why should the relaxation occur in just the right way to produce the observed value? There is, of course, another possibility, one that many physicists find deeply uncomfortable, even disturbing, and yet one that has gained considerable traction over the past several decades. This is the anthropic approach, the suggestion that the cosmological constant is not derived from fundamental theory at all, but is instead selected by the conditions necessary for observers to exist. The idea is simple in outline, though controversial in implication. If the cosmological constant could take many different values in different regions of the universe, or in different members of some vast ensemble of universes, then only those regions with a sufficiently small vacuum energy would permit the formation of galaxies, stars, planets, and life. We observe a small cosmological constant, not because physics demands it, but because we could not exist to observe anything else. This reasoning traces back to the pioneering work of Steven Weinberg in the late 1980s. Weinberg, one of the architects of the Standard Model and a Nobel laureate, was troubled by the vacuum catastrophe. He recognized that conventional physics offered no explanation for the smallness of the cosmological constant, and so he asked a different question. What values of the cosmological constant are compatible with the existence of observers? The calculation is elegant. If the cosmological constant were too large and positive, the universe would have expanded too rapidly for gravitational structures to form. Matter would never have clumped into galaxies, stars would never have ignited, planets would never have coalesced from circumstellar disks. Life, at least as we understand it, would be impossible. On the other hand, if the cosmological constant were too large and negative, the universe would have recollapsed before complexity could emerge. The window for observers is narrow, and Weinberg showed that the observed value of the cosmological constant lies within this window, perhaps 1 or 2 orders of magnitude below the upper anthropic bound, but certainly within the range where galaxies can form and life can arise. This was a remarkable result. At a time when most physicists assumed the cosmological constant was exactly 0, Weinberg predicted that if it were non-zero, it would have a value roughly comparable to the matter density of the universe. This prediction was made years before the supernova observations that revealed cosmic acceleration. When those observations came, they found a cosmological constant within Weinberg's anthropic window. The coincidence was striking. The prediction had been vindicated, but the implications were unsettling. For the anthropic argument to work, you need a mechanism that allows the cosmological constant to vary. If there is only one universe, with one fixed value of the vacuum energy, then the argument has no explanatory power. You're simply asserting that the value is what it is because otherwise we would not be here to observe it. This is tautological, a restatement of the observation rather than an explanation of it. But if there are many regions of space, or many universes altogether, each with a different value of the cosmological constant, then the anthropic selection becomes meaningful. We find ourselves in a region with a hospitable vacuum energy because those are the only regions where observers can exist. This is where the landscape of string theory enters the story. String theory, the leading candidate for a unified theory of all fundamental forces, does not predict a unique vacuum state. Instead, it predicts an astronomical number of possible vacua, a landscape of solutions, each with its own values of the fundamental constants, its own particle content, its own cosmological constant. Estimates of the number of vacua range from 10 to the 500 to 10 to the hundreds of thousands, numbers so vast that they defy human intuition. In this landscape, almost any value of the cosmological constant is realized somewhere. The small value we observe is not special from the perspective of fundamental physics. It is simply one point among a near-infinite multitude. If this picture is correct, then the vacuum catastrophe dissolves, not because we have calculated the cosmological constant from first principles, but because we have abandoned the expectation that such a calculation is possible. The cosmological constant is an environmental parameter, like the distance from Earth to the Sun, rather than a derivable quantity like the fine structure constant. We observe the value we do because it is compatible with our existence. Other values exist in other regions of the landscape, but we are not there to see them. This is deeply unsatisfying to many physicists. It feels like giving up. The goal of physics has always been to explain, to derive, to predict. The anthropic approach seems to replace explanation with selection, derivation with statistics. If the cosmological constant cannot be calculated, then what else might be anthropically selected? The masses of the elementary particles, the strengths of the fundamental forces. Where does the explanatory ambition of physics end and the anthropic shrug begin? And yet, the anthropic perspective has its defenders. They point out that science has often had to abandon certain expectations in the face of evidence. We once hoped to explain why Earth orbits at its particular distance from the Sun. We now understand that this distance is contingent. the result of chaotic processes in the early solar system, and that many other distances are realized around other stars. The question, why this distance, has no deep answer. It is simply where we happen to be. Perhaps the cosmological constant is similar. Perhaps we must accept that some quantities are environmental, not fundamental. The debate continues. It is one of the great philosophical fault lines in contemporary physics, dividing those who insist on a dynamical or symmetry-based explanation from those who accept the anthropic alternative. Neither side has a decisive argument. The landscape of string theory remains conjectural. We have no direct evidence for other vacua, no experimental probe of the multiverse. The anthropic reasoning is consistent but unfalsifiable in its strongest form, and the vacuum catastrophe persists, indifferent to our theoretical preferences. Meanwhile, the observational evidence grows. The DESI collaboration, the dark energy spectroscopic instrument, represents the latest and most ambitious effort to map the expansion history of the universe. DESI is installed at the Nicholas U. Mail Telescope on Kitt Peak in Arizona, a 4-meter reflector fitted with 5,000 robotic fiber positioners that can acquire spectra of thousands of galaxies and quasars in a single exposure. The survey is cataloguing tens of millions of objects, tracing the distribution of matter across billions of light years, measuring the imprint of baryon acoustic oscillations, the frozen sound waves from the early universe, on the large-scale structure of the cosmos. Baryon acoustic oscillations are a powerful tool. In the hot, dense plasma of the early universe, sound waves propagated through the mixture of matter and radiation. These waves left their mark on the distribution of matter, creating a characteristic scale, about 500 million light-years in today's universe, that appears as a slight excess of galaxy pairs at that separation. This scale serves as a standard ruler, a cosmic yardstick that can be measured at different redshifts to trace the expansion history. By comparing the apparent size of this ruler at different epochs, cosmologists can reconstruct how the universe has expanded over time and constrain the properties of dark energy. The first DESI results, released in 2024, were tantalizing. The data suggested that the equation of state of dark energy, the parameter W that relates its pressure to its energy density, might not be constant. In a pure cosmological constant model, W is exactly -1 at all times, but the DESI measurements, combined with other cosmological probes, hinted that W might have been different in the past, evolving from a value less negative than -1 at early times toward -1, or even beyond at late times. This is precisely the behavior expected in quintessence models, where dark energy is a dynamical field rather than a static vacuum contribution. The statistical significance of these hints is modest, roughly 2 to 3 sigma, depending on the analysis and the combination of datasets. This is enough to provoke interest, but not enough to claim discovery. Physicists have learned, sometimes painfully, that signals at this level can evaporate with more data. The history of cosmology is littered with tantalizing hints that did not survive scrutiny. The anomalous microwave background features, the apparent tensions in the Hubble constant, the possible signs of cosmic birefringence. Each has generated excitement, papers, conferences, and eventually either confirmation or dissolution. The DESI hints must run the same gauntlet. Yet even the possibility of evolving dark energy opens new vistas. If the vacuum is not static, then the catastrophe takes on a different character. Perhaps the mechanisms that set the vacuum energy are themselves dynamical, evolving over cosmic history, responding to the changing conditions of the universe. Perhaps the smallness of the cosmological constant today is not a matter of fine-tuning at the Planck epoch, but the result of a long relaxation process that only recently reached its current state. Or perhaps the apparent evolution is not in the vacuum energy at all, but in some other component of the dark sector, a new field interacting with dark matter or altering the expansion rate through unfamiliar physics. These possibilities are being explored in theoretical models around the world. They appear in papers on early dark energy, on phantom crossing, on coupled dark sectors, on modifications of gravity at cosmological scales. The landscape of theoretical ideas is as rich and varied as the observational landscape is deep. But without decisive data, the theories proliferate unconstrained. We need more observations, more precise measurements, more stringent tests, and so the survey continues. DESI collects light from ever more galaxies. The Vera C. Rubin Observatory, still being commissioned in the mountains of Chile, prepares to survey the entire southern sky every few nights, detecting billions of galaxies and millions of supernovae, probing dark energy with an unprecedented combination of depth and breadth. The Euclid Space Telescope, launched by the European Space Agency, orbits the Sun at the second Lagrange point, mapping the shapes of galaxies to detect the subtle distortions caused by gravitational lensing, distortions that reveal the distribution of dark matter and the geometry of space. The Nancy Grace Roman Space Telescope, under construction for a future launch, will add yet another window on the dark universe. Each of these instruments brings new capabilities. Each generates data measured in petabytes, analysed by algorithms running on supercomputers, scrutinised by collaborations spanning continents. The era of precision cosmology is also the era of industrial-scale science, of international teams and decades-long projects and budgets in the billions. The questions may be ancient. Why does the universe behave as it does? What is the nature of the vacuum? Why is there something rather than nothing? But the methods are thoroughly modern. And still, the vacuum catastrophe looms. It is there in the background of every measurement, every model, every interpretation. When cosmologists fit their data to theoretical curves, they include the cosmological constant as a free parameter, adjusting it to match the observations. But they cannot derive it. They cannot explain it. They cannot predict it from first principles. The value that emerges is always the same, a number so small, so finely balanced, so inexplicable that it haunts the field like a ghost. Some physicists have suggested that the resolution of the vacuum catastrophe will require a revolution as profound as the quantum revolution itself. The problem, they argue, is not a detail to be patched within the existing framework. It is a signal that the framework itself is incomplete, that our understanding of quantum field theory and general relativity is missing something essential. Perhaps the very concept of vacuum energy needs to be rethought. Perhaps space and time are not fundamental but emergent, arising from deeper structures that do not respect our current notions of energy and geometry. Perhaps the distinction between empty space and filled space is illusory, a byproduct of our limited perspective. These are radical ideas. They challenge the foundations of physics as it has been practiced for a century, and they are frustratingly vague, more philosophy than calculation, more intuition than prediction. The physicists who advocate for such revolutions cannot yet produce the new theory they seek. They gesture toward horizons they cannot reach. They speak of paradigm shifts without providing the paradigm. But perhaps that is how revolutions happen, not with a sudden flash of insight fully formed, but with a slow accumulation of puzzles, anomalies, and failed attempts that eventually becomes unbearable. The vacuum catastrophe has been accumulating for 50 years. The weight of the problem grows with each passing decade, and somewhere, in some office or classroom or late-night conversation, the seeds of the next breakthrough may already be germinating. Ideas that seem outlandish today, but will seem obvious in retrospect. For now, we have only the data and the mystery. We have a universe accelerating in its expansion, driven by an energy whose origin we cannot explain. We have theories that predict too much, observations that reveal too little, and a gap between them that spans more than 100 orders of magnitude. We have hints of evolution, whispers of dynamics, suggestions that the vacuum may not be as static as we assumed. And we have the stubborn persistence of the problem, resisting every attempt at solution, humbling every theorist who approaches it. The empty room is still humming. The hum is quiet, too quiet for any instrument to measure directly, but its consequences shape the fate of galaxies and the future of the cosmos. We know the hum is there, we measure its effects, we simply cannot explain why it sounds the way it does. And so we stand at the edge of what is known, peering into a darkness that is not the absence of light, but the absence of understanding. The instruments grow more powerful, the data grow more precise, and the mystery deepens. It was in this climate of refined confusion that a name began to appear with increasing frequency in the footnotes and citations of cosmological papers. Steven Weinberg, already a towering figure in theoretical physics, a Nobel laureate for his work on the unification of electromagnetic and weak forces, had turned his formidable intellect toward the cosmological constant problem. And in 1987, he published a paper that would reshape the entire conversation. Not by solving the problem, but by suggesting that perhaps it could not be solved in the traditional sense. Perhaps the question itself was wrong. Weinberg's argument was deceptively simple. Imagine he proposed that the cosmological constant is not a fixed quantity determined by some deep principle of physics. Imagine instead that it varies, that across the vast, perhaps infinite expanse of existence, different regions of space have different values of vacuum energy. Some regions would have enormous positive values, space ripping itself apart in runaway expansion before any structures could form. Others would have large negative values, collapsing almost instantly into gravitational catastrophe, and others still would have values somewhere in between, tiny, finely balanced, capable of allowing the slow gravitational collapse that forms galaxies, stars, planets, and eventually observers who might wonder about the nature of the vacuum. This was the anthropic argument. It was not a calculation in the traditional sense. It was a selection effect, a filter applied by the very fact of our existence. We find ourselves in a region of the cosmos where the cosmological constant happens to be small, not because of any deep physical principle, but because we could not exist anywhere else. The regions with enormous vacuum energy have no one to measure them. The regions with the right value, the tiny, improbable value, are the only ones that produce physicists. Weinberg went further. He did not merely propose this possibility, he calculated its consequences. If the anthropic argument were correct, if the cosmological constant were a random variable selected by the requirement that observers exist, what value should we expect to find? He worked through the statistics, the probabilities, the conditions necessary for galaxies to form and stars to live long enough for life to arise, and he arrived at a prediction. The cosmological constant should be small, but not zero. It should be roughly comparable to the matter density of the universe at the present epoch, give or take an order of magnitude or two. It should be, in other words, almost exactly what observers would later measure. This was remarkable. In 1987, a full 11 years before the supernova measurements that confirmed cosmic acceleration, Weinberg had predicted that the cosmological constant would be non-zero and had estimated its approximate value. When the observations came in, his prediction was vindicated. The measured value fell squarely within the range his anthropic reasoning had suggested. But vindication is not the same as explanation. The scientific community's reaction to Weinberg's argument was deeply divided, and that division persists to this day. For some physicists, the anthropic approach was a revelation, a way of understanding fine-tuning problems that had seemed utterly intractable. For others, it was an abdication, a surrender of the physicist's duty to explain phenomena in terms of underlying principles. To invoke the anthropic principle, they argued, was to say, it is what it is because otherwise we wouldn't be here to ask. That might be true, but it explained nothing. It predicted nothing new. It was, in the words of one critic, the last refuge of the desperate theorist. The debate cut to the heart of what physics is supposed to accomplish. For centuries, the great triumphs of the discipline had come from deriving observed quantities from deeper principles. Newton explained Kepler's laws. Maxwell unified electricity, magnetism, and light. Einstein derived the precession of Mercury's orbit from the geometry of space-time. The pattern was always the same: observation, puzzlement, theoretical breakthrough, understanding. The cosmological constant problems seemed to demand the same treatment. Surely there was some mechanism, some symmetry, some principle waiting to be discovered that would explain why the vacuum energy is precisely what it is. But what if there wasn't? What if some quantities in physics are environmental accidents, selected not by equations but by the conditions necessary for observers to exist? This was the unsettling possibility that Weinberg's argument raised, and it became far more concrete with the rise of the string theory landscape. String theory, for decades, had promised to be the ultimate theory of everything, a framework that would uniquely determine all the constants of nature, all the particles and forces, from a single mathematical structure. The hope was that string theory would leave no free parameters. Given the theory, you could calculate everything. The cosmological constant would emerge as a prediction, not an input. That hope collapsed in the early 2000s. As string theorists explored the mathematical possibilities of their framework, they discovered not a unique solution, but a vast multiplicity of solutions. The landscape of string theory, as it came to be called, contained an almost inconceivable number of possible vacuum states. Estimates range from 10^500 to numbers even larger. Each vacuum corresponded to a different configuration of the extra dimensions required by string theory. different ways the fundamental ingredients could be arranged, and each vacuum had its own value of the cosmological constant. For some physicists, this was a catastrophe. The dream of unique predictivity had evaporated. String theory, rather than explaining the constants of nature, seemed to contain every possible set of constants. It explained everything, and therefore nothing. But for others, the landscape was precisely what the anthropic argument required. If there existed a vast number of different vacua, each with its own cosmological constant, then the selection effect Weinberg had described made perfect sense. Most vacua would be inhospitable to life. A tiny fraction, but still an enormous absolute number, given the size of the landscape, would have cosmological constants in the anthropically allowed range, and we would necessarily find ourselves in one of those. This fusion of the string landscape and the anthropic principle became known as the multiverse hypothesis. It proposed that our observable universe is just one bubble in a vast, perhaps infinite collection of bubbles, each with its own physical constants, its own laws derived from the same underlying string theory but realized in different ways. We cannot observe the other bubbles. We cannot communicate with them. We can only infer their existence from the theoretical framework and use anthropic reasoning to explain why our bubble has the properties it does. The multiverse hypothesis remains deeply controversial. It makes no directly testable predictions. It invokes entities, the other bubbles, that are in principle unobservable. It seems to violate the very essence of empirical science, which demands that theories be tested against observation. And yet it is not entirely untestable. If the multiverse exists, there should be statistical correlations in the values of physical constants. We should find ourselves in a typical anthropically allowed universe, not an atypical one. There should be signatures, perhaps, in the distribution of constants that could be compared to multiverse predictions. These arguments continue. Conferences are held, papers are written, tempers occasionally flare. The multiverse is either the inevitable conclusion of our best theories or the abandonment of scientific method, depending on whom you ask. But one thing is clear: the cosmological constant problem has not been solved. Even if the anthropic multiverse explanation is correct, it does not constitute a derivation from first principles in the traditional sense. It does not tell us why the underlying probability distribution over cosmological constants takes the form it does. It does not explain the mechanism that produces the landscape. It shifts the mystery rather than resolving it. And so physicists continue to search for alternatives. Some refused to accept the anthropic argument on philosophical grounds and devoted their careers to finding dynamical mechanisms that could drive the vacuum energy to zero, or to some small predictable value, without invoking selection effects. Others embraced the multiverse but sought to understand its structure better, hoping that deeper analysis would yield new predictions. Still others stepped back from the problem entirely, focusing on aspects of physics that seemed more tractable, waiting for new data or new ideas to break the deadlock. The waiting was not entirely passive. Throughout the 2010s, cosmological observations continued to improve. The Planck satellite mapped the cosmic microwave background with unprecedented precision. Galaxy surveys measured the distribution of matter on the larger scales. The expansion history of the universe was traced back through billions of years using multiple independent techniques. And always the same picture emerged: a universe dominated by dark energy, expanding at an accelerating rate, with a cosmological constant that stubbornly refused to change. But there were hints, small tensions, discrepancies at the margins of uncertainty that might be statistical flukes or might be the first whispers of something new. The most famous of these was the Hubble tension, a disagreement between different methods of measuring the current expansion rate of the universe. Local measurements using supernovae and Cepheid variable stars consistently gave higher values than the rate inferred from the cosmic microwave background. The discrepancy was small, just a few percent, but it persisted. It grew more significant as the measurements improved, and it resisted easy explanation. Was the Hubble tension a sign that the cosmological constant model was incomplete? Was there something wrong with the early universe physics? Was dark energy more complicated than a simple constant? The questions multiplied, but definitive answers remained elusive, and then came DESI. The dark energy spectroscopic instrument, mounted on a telescope in the Arizona desert, began its survey in 2021. Its mission was ambitious: to map the three-dimensional distribution of tens of millions of galaxies and quasars, creating the most detailed picture ever made of the universe's structure. By measuring how that structure evolved over cosmic time, DESI could trace the expansion history with extraordinary precision. It could test whether dark energy was truly constant or whether it changed, whether the vacuum was static or dynamic. The survey would take years, the analysis would take longer. But preliminary results began to emerge in 2024, and they sent a ripple through the cosmological community. The data suggested, tentatively with caveats and error bars, that dark energy might not be constant. Its density appeared to have changed over time. In the early universe it was slightly larger, in the recent universe slightly smaller. The change was subtle, perhaps a few percent, but it was there in the data. If confirmed, this would be a revolution. A static cosmological constant had been the working assumption for a quarter century. It was the simplest explanation, the most economical, the most consistent with the theoretical framework. A changing dark energy would demand new physics, it would open new questions, and it would profoundly affect the vacuum catastrophe. Consider what a changing cosmological constant would mean. If vacuum energy is not fixed but evolves, then the traditional formulation of the problem, the discrepancy between the calculated and observed values at a single moment, becomes less well defined. The vacuum energy at the Planck scale might be enormous, as quantum field theory predicts, but it could then decrease over cosmic time through some dynamical mechanism. The residual value we observe today would be the result of billions of years of evolution, not a fixed constant of nature. This is the domain of quintessence. The name, borrowed from Aristotle's fifth element, the substance of the heavens, incorruptible and eternal, refers to a hypothetical field that permeates all of space, much like the Higgs field, but whose energy density changes as the universe expands. In quintessence models, the cosmological constant is replaced by this dynamical field, and the apparent acceleration of the universe is driven by the field's current configuration. Quintessence had been proposed decades earlier, but it had never been more than a theoretical curiosity. The data did not require it. A simple constant fit the observations just as well, and simplicity is a powerful criterion in physics. But if DESI was right, if the data genuinely favoured evolution over constancy, then quintessence would move from the margins to the centre of cosmological attention. The DESI results, announced in April 2024, were not definitive. The statistical significance was suggestive but not overwhelming. The systematic uncertainties were still being explored, and any claim of evolving dark energy would need to be confirmed by independent surveys. Euclid, the Roman Space Telescope, the Vera Rubin Observatory's upcoming campaign. Science proceeds through replication and cross-checking, not single announcements. But the community was electrified. Papers appeared within days, exploring the implications, fitting models, proposing mechanisms. Could quintessence explain the Hubble tension as well? Could it connect to other anomalies, other hints of new physics that had accumulated over the years? The theoretical landscape shifted. Ideas that had been dormant were revived. Physicists who had spent careers on other problems suddenly found themselves reading about dynamical dark energy. And underlying all of this ferment was a deeper question. Even if dark energy evolves, does that solve the vacuum catastrophe, or does it merely transform it? The answer, frustratingly, is the latter. A dynamical field replacing the cosmological constant does not eliminate the fine-tuning problem, it relocates it. Now, instead of asking why the vacuum energy is so small, we must ask why the quintessence field is configured in precisely the way needed to produce tiny dark energy today. The field must roll down its potential energy landscape at exactly the right rate, starting from initial conditions that are themselves unexplained. The coincidence problem, the observation that dark energy and matter densities are comparable at the present epoch, becomes a question about the dynamics of the field rather than the value of a constant. But it remains a question. Some physicists see this as progress. A dynamical problem is at least a problem with moving parts, with equations that can be written and solved, with predictions that can be tested. A static coincidence offers no handles, no mechanisms, no routes to deeper understanding. Quintessence, if it exists, can be studied. Its properties can be constrained, its interactions can be explored, and perhaps, in that exploration, hints of the underlying physics will emerge. Others are more skeptical. They note that quintessence models typically introduce new fine-tuning problems of their own. The potential energy function of the field must be extraordinarily flat to allow for slow evolution over cosmic timescales. The mass of the quintessence field must be absurdly light, lighter than any known particle, lighter than the limits imposed by experiments on other light fields. The model explains one mystery by invoking another. This is the pattern that has repeated for 50 years. Each proposed solution to the vacuum catastrophe introduces new puzzles, new parameters, new questions. The problem is hydra-headed. Cut off one aspect and two more grow back. The theorists who work on it know this. They describe the experience as humbling, frustrating, sometimes maddening. And yet they continue. The problem is too important to abandon, too central to our understanding of the universe, too tantalizing in its hints that something fundamental is missing. In laboratories around the world, experiments continue to probe the vacuum. Measurements of the Casimir effect, the force between closely spaced metal plates caused by the exclusion of certain vacuum fluctuations, test our understanding of zero-point energy at scales far smaller than cosmological observations can reach. Particle accelerators search for new fields, new symmetries, new physics that might connect to dark energy. Gravitational wave detectors listen for signals that could constrain alternative theories of gravity. The vacuum is being poked and prodded from every direction, with every tool available, and still it keeps its secrets. The hum of the empty room, that infinite reservoir of quantum energy, remains inexplicable. The most precise theories in the history of science fail to account for its observed volume by a factor so large that writing it down strains the imagination. The cosmological constant, whether static or evolving, stands as a monument to our ignorance, not the comfortable ignorance of unexplored territory, but the uncomfortable ignorance of a problem we have worked on intensely and failed to solve. Perhaps the next generation of observations will provide the crucial clue. Perhaps DESI's hints of evolving dark energy will be confirmed and will point toward new physics. Perhaps some young theorist, working in obscurity today, will have the insight that unlocks the puzzle. Or perhaps the anthropic multiverse is indeed the answer, and we must accept that some questions have no deeper explanation, that we live in this universe because we could not live in another. The story is not over. The instruments are still collecting data. The theorists are still calculating. The vacuum is still there, humming at a frequency we cannot hear, shaping the cosmos in ways we can barely comprehend. And somewhere in that hum, in that vast discrepancy between prediction and observation, lies a truth we have not yet grasped. The truth, whatever it is, has eluded some of the finest minds of the past half-century. It has resisted the most sophisticated mathematical frameworks ever devised. It has mocked the confidence of theoretical physics, humbled its practitioners, and turned what should have been a straightforward calculation into a generational quest. To understand why every attempt to derive the correct value of the vacuum energy from first principles has failed, we must walk through those attempts themselves, not as abstract failures, but as serious, sustained efforts by brilliant people who believed they were on the verge of solving the problem. We must feel the weight of their frustration, appreciate the ingenuity of their approaches, and confront the stubborn reality that defeated each one in turn. The first and most natural approach was simply to wait. In the early days, when the discrepancy was first recognized, many physicists assumed it would resolve itself. The history of physics is filled with apparent contradictions that melted away as theories matured, as calculations were refined, as new particles or principles were discovered that reconciled seemingly irreconcilable numbers. The ultraviolet catastrophe of classical blackbody radiation, that embarrassing prediction that heated objects should radiate infinite energy at high frequencies, had been solved by the quantum hypothesis. The divergences in quantum electrodynamics, those infinite quantities that appeared in every calculation, had been tamed by the renormalization procedure. Perhaps the vacuum energy problem would yield to similar treatment. Perhaps some forgotten contribution, some overlooked symmetry, some clever mathematical trick would make the enormous quantum contribution cancel against something else, leaving behind the tiny residual that observations demand. But the wait proved fruitless. The problem did not resolve itself. As calculations grew more sophisticated, as quantum field theory was tested to extraordinary precision in particle physics experiments, the enormous zero-point energy remained stubbornly present in the equations. The vacuum was not going to subtract itself away through some accounting trick. Its energy was real, present in every formula, verified by experiments like the Casimir effect. The wait for natural resolution stretched into years, then decades, and eventually it became clear that waiting was not a strategy. Something more active was needed. The second approach was supersymmetry. This was not invented to solve the vacuum energy problem. It arose from attempts to unify the forces of nature and to explain certain puzzling features of particle physics, but it seemed for a time to offer a miraculous solution. In supersymmetry, every known particle has a partner. Every fermion, those particles of matter like electrons and quarks, is paired with a boson, a force-carrying particle, and every boson is paired with a fermion. The mathematics of this pairing is exquisite, and it has a remarkable consequence for vacuum energy. Fermions contribute negative zero-point energy, while bosons contribute positive zero-point energy. If the symmetry is exact, if every particle has a partner of exactly equal mass, the contributions cancel perfectly. The vacuum energy becomes exactly zero. This was thrilling. An entirely different theoretical program motivated by entirely different concerns seemed to solve the cosmological constant problem as a bonus. Physicists working on supersymmetry felt they were onto something profound. The equations were beautiful, the cancellation was perfect, and the theory made predictions that could be tested at particle accelerators. If supersymmetric partners existed at accessible energies, they would be produced and detected, and the vacuum energy problem would be solved along with many others. But nature, as it so often does, had other plans. Supersymmetry, if it exists, is not exact. We know this because we have never detected a supersymmetric partner particle. The electron does not have a selectron of equal mass. The quark does not have a squark we can produce in colliders. If supersymmetry exists, it must be broken. The partner particles must be heavier than their known counterparts, too heavy to have been produced in experiments so far. This breaking is not a minor detail. It destroys the perfect cancellation that made supersymmetry so attractive as a solution to the vacuum problem. When supersymmetry breaks, the boson and fermion contributions to vacuum energy no longer balance. A residual energy remains, and that residual depends on the scale of supersymmetry breaking, on how much heavier the partner particles are than the particles we know. The problem is that the scale of supersymmetry breaking must be at least as high as the energies explored by the Large Hadron Collider, which has found no evidence for supersymmetric particles. At those scales, the residual vacuum energy is still enormous by cosmological standards, perhaps not 10 to the power of 122 times too large, but still many tens of orders of magnitude too big. Supersymmetry softens the problem without solving it. It trades an absurd discrepancy for merely a gigantic one, and even this modest improvement comes at a cost. The theory becomes increasingly contrived as the symmetry-breaking scale is pushed higher, requiring additional mechanisms and parameters to explain why the breaking occurs where it does and not elsewhere. The third approach was to invoke a different kind of symmetry altogether. If supersymmetry couldn't make the vacuum energy exactly zero, perhaps some other principle could. Physicists searched for symmetries that would force the cosmological constant to vanish, not through cancellation between different contributions, but through a deeper structural requirement of the theory itself. Scale invariance was one candidate. The idea that the fundamental laws of physics look the same at all scales, whether you zoom in or zoom out. In a perfectly scale invariant theory, there can be no preferred scale, and the cosmological constant, which sets a scale for spacetime curvature, would have to be zero. But scale invariance is manifestly broken in the world we observe. Particles have definite masses, atoms have definite sizes, galaxies form at definite scales. If scale invariance exists at some fundamental level, it must be broken by the time physics reaches the energies and distances we can probe, and the breaking will generally induce a non-zero cosmological constant. The same pattern repeated, a symmetry that could solve the problem in its exact form, but whose necessary breaking regenerates the problem in a different guise. Others tried to construct models where the cosmological constant was zero by construction, theories where, for mathematical or conceptual reasons, the vacuum energy simply could not contribute to gravity. These efforts often invoked modifications to general relativity itself, changes to the rules that govern how energy and momentum curve spacetime. Perhaps gravity doesn't couple to vacuum energy in the same way it couples to ordinary matter. Perhaps there is a filtering mechanism, a cosmic censorship that shields the gravitational equations from the infinite energy of the quantum vacuum. Such ideas are not without precedent. In classical electromagnetism, the absolute value of the electric potential has no physical meaning, only potential differences matter. Perhaps vacuum energy is similar, an absolute quantity that cannot be measured and does not affect the dynamics of the universe. But the attempts to implement this idea mathematically proved treacherous. General relativity, as Einstein formulated it, responds to all forms of energy. The vacuum energy appears in the stress energy tensor, and the stress energy tensor determines the curvature of space-time. To prevent this coupling requires radical surgery on the theory, and every surgical procedure that was attempted either broke something else, destroying the theory's empirical successes, or smuggled the cosmological constant back in through a different door. The fourth approach, and perhaps the most ambitious, was to seek the solution in a theory of quantum gravity. General relativity is a classical theory. It does not incorporate quantum mechanics. Quantum field theory, meanwhile, does not incorporate gravity. The vacuum energy problem lives at the intersection of these two frameworks, and perhaps, some reasoned, it cannot be solved until the frameworks are unified. Perhaps the full theory of quantum gravity, whatever it turns out to be, will automatically produce a small cosmological constant. Perhaps the paradox is an artifact of our incomplete understanding, a clash between approximations that will dissolve when we see the complete picture. String theory was the most developed candidate for such a unification. In string theory, particles are not point-like objects but tiny vibrating strings, and the different modes of vibration correspond to different particles. The theory naturally incorporates gravity, and in its early years, there was hope that it might explain the values of all physical constants, including the cosmological constant. The constants would emerge from the geometry of extra dimensions, from the way strings wrap around compact spaces, from the particular vacuum state the universe chose to inhabit out of a vast landscape of possibilities. But as string theory matured, it became clear that the landscape was too vast. There were not just a few possible vacuum states, but an almost incomprehensibly large number, 10 to the power of 500 or more, each with different values for the fundamental constants, including the cosmological constant. The theory did not predict a single value. It accommodated essentially any value. This was the origin of the multiverse picture, the idea that all possible vacua might be realized somewhere in an eternally inflating cosmos, and that we find ourselves in one compatible with our existence. For many physicists, this was not a solution but an abdication. String theory, in this incarnation, did not explain the vacuum energy. It merely noted that some vacua would have small values and that we must inhabit one of them. The anthropic reasoning that followed was logically coherent but scientifically unsatisfying. It made no predictions beyond the requirement of compatibility with observers. It offered no mechanism, no dynamics, no deeper principle. The cosmological constant remained a brute fact, unexplained by fundamental physics, selected only by the accident of where we happen to be. Still, the theoretical efforts continued. New ideas emerged, building on older ones, combining elements in novel ways. Some physicists pursued the idea of vacuum energy relaxation, mechanisms by which a large initial cosmological constant would dynamically decrease over time, settling eventually to a small value. The quintessence models mentioned earlier were one version of this, but there were more exotic variants. Perhaps the vacuum energy was not constant at all, but was slowing, bleeding away through some process we had not yet identified. Perhaps the universe had self-tuning properties, adjusting its effective cosmological constant in response to its contents. One class of models invoked what were called adjustment mechanisms. These were dynamical fields or new gravitational physics that would automatically cancel the vacuum energy, no matter how large it became. If you added vacuum energy to the universe, the adjustment field would respond by subtracting an equal amount, leaving a net contribution of 0 or nearly 0. The idea was appealing, a kind of cosmic thermostat that kept the vacuum energy at a habitable level, regardless of what quantum field theory predicted. But there was a deep obstacle, identified by Steven Weinberg and others in the 1980s and never subsequently overcome. For an adjustment mechanism to work, it must couple to the vacuum energy, which means it must distinguish vacuum energy from other forms of energy. Ordinary matter, radiation, dark matter, these contribute to the expansion of the universe, and we need them to do so. Without their gravitational effects, The observed cosmos would not match our measurements. The adjustment mechanism must cancel the quantum zero-point energy without cancelling everything else. It must be exquisitely selective, responding only to the vacuum contribution and ignoring the rest. This selectivity is extraordinarily difficult to achieve in a consistent theory. Vacuum energy, in the equations of physics, looks just like any other form of constant energy density. It has the same effect on space-time curvature, the same place in the stress-energy tensor, the same relationship to the expansion rate of the universe. An adjustment mechanism that cancelled vacuum energy would generically cancel all constant energy densities, leading to predictions that violate observations. The attempts to construct selective mechanisms either failed outright or required such elaborate fine-tuning that they merely displaced the problem rather than solving it. By the turn of the millennium, a certain resignation had set in among theoretical physicists. The vacuum catastrophe had resisted every attack, supersymmetry had failed, scale invariance had failed, adjustment mechanisms had failed, string theory had led to the multiverse, which some viewed as progress and others as the end of explanatory physics. The community fractured into camps, those who continued to seek a dynamical solution, those who embraced the anthropic multiverse, those who pursued modifications to gravity, and those who simply set the problem aside, working on questions that seemed more tractable while hoping that future breakthroughs would illuminate the path forward. And yet the problem would not go away. It lurked in the background of every discussion of cosmology, every calculation of particle physics, every contemplation of the deep structure of reality. The observed cosmological constant was there, driving the acceleration of the universe, shaping its ultimate fate. The predicted vacuum energy was there too, enormous and undeniable, written into the foundations of quantum field theory. The gap between them was not a minor discrepancy, but an absolute chasm, a failure of understanding so complete that it called into question the entire framework of modern physics. Some physicists began to wonder if the problem was not merely difficult, but impossible. Impossible, at least, within the current theoretical paradigm. Perhaps solving the vacuum catastrophe required not just new ideas, but a revolution comparable to the transition from classical physics to quantum mechanics, a transformation so profound that it would reshape our understanding of space, time, matter, and energy. Perhaps the very concepts we were using, vacuum, energy, cosmological constant, were emergent rather than fundamental, rough approximations that broke down at deeper levels of description. Perhaps the question, why is the cosmological constant so small, was like asking, why does the Earth rest on a turtle? A question that makes sense within a certain worldview, but dissolves when the worldview is abandoned. This is a radical position, and most physicists are not yet ready to embrace it. The successes of quantum field theory and general relativity are too extensive, too precise, too thoroughly verified to discard lightly. These frameworks describe nature with astonishing accuracy in their respective domains. The problem is not that they are wrong, but that they are incomplete, or that their domains overlap in ways we do not understand, or that some hidden assumption, so natural that it has never been questioned, is leading us astray. One such assumption concerns the nature of space-time itself. In both quantum field theory and general relativity, space-time is treated as a continuous manifold, smooth at every scale, infinitely divisible. But there are reasons to suspect that this picture breaks down at the Planck scale, the unimaginably tiny distance at which quantum gravitational effects should become important. Perhaps space-time is fundamentally discrete, composed of indivisible atoms of space, finite in number and limited in energy. If so, the calculation of vacuum energy might need to be revisited. The sum over modes might be naturally finite, not because of an arbitrary cutoff, but because there are only finitely many modes to sum over. The infinite tower of contributions that leads to the 10 to the 122 discrepancy might be an artifact of the continuum approximation, a mathematical ghost that disappears in the true theory. Loop quantum gravity, one approach to quantum gravity that treats space-time as fundamentally discrete, has explored this possibility. In loop quantum gravity, space is built from networks of links and nodes, and area and volume are quantized. They come in discrete chunks rather than varying continuously. Some researchers have hoped that this discreteness might resolve the vacuum energy problem, that the calculations would yield finite, reasonable answers when performed in the correct quantum gravitational context. But the results have been inconclusive. Loop quantum gravity is still under development, and calculations of vacuum energy in this framework are technically challenging. Different approaches and approximations yield different answers, and there is no consensus on what the full theory predicts. The discreteness of spacetime might help, or it might not. It might produce a small cosmological constant or zero, or some other value that depends on parameters we have not yet determined. The hope persists, but the proof remains elusive. Other approaches have questioned the assumption that gravity and quantum field theory must be reconciled in the straightforward way that physicists have assumed. Perhaps gravity is not a quantum field at all. Perhaps it is fundamentally classical, or emerges from underlying thermodynamic principles, or obeys rules we have not yet imagined. These heterodox ideas are difficult to develop into complete theories, and they often run afoul of known physics, but they keep alive the possibility that the vacuum catastrophe is pointing towards something deeply unexpected. What is certain is that the problem has transformed theoretical physics. It has shifted attention from the particle physics frontier to the cosmological frontier, from colliders to telescopes, from high energies to the emptiness between galaxies. It has forced physicists to confront questions they once dismissed as philosophical. Why are the constants of nature what they are? Can fundamental physics explain everything, or are some things simply contingent? What does it mean to understand the universe? The vacuum catastrophe is not merely a technical puzzle. It is a mirror in which physics sees its own limitations. For a century, physicists have pursued the dream of a final theory, a complete description of nature from which all phenomena would follow. That dream was always aspirational, always a horizon receding as knowledge advanced. But the vacuum energy problem makes the horizon feel more distant than ever. It suggests that our best theories, for all their successes, are missing something essential. It whispers that the universe is stranger than we have allowed ourselves to believe. And still the observations continue. The telescopes keep watching. The data keep accumulating. The vacuum, that most intimate aspect of reality, the thing that is everywhere and nowhere, the hum beneath all existence, keeps its counsel. It reveals just enough to tantalize, just enough to frustrate, just enough to keep the physicists working through the night, scribbling equations on whiteboards, running simulations on computers, arguing at conferences and in journal pages over what it all means. Somewhere in that vast discrepancy between theory and observation, between 10 to the power of 122 and 1, lies a secret. We do not yet know its nature. We do not know if we are close to finding it, or if it will take another century, another revolution, another way of thinking we cannot yet imagine. What we know is that the problem is real, that it matters, that it will not go away until it is solved, or until we learn to ask better questions. The vacuum energy, that ghost in the machine of physics, awaits its explanation. And until that explanation comes, the humming persists, vast, incomprehensible, and utterly unexplained. The humming persists, but we do not simply wait for revelation. We build instruments, we refine measurements. We push observation to its limits, hoping that nature will give us a clue, a hint, a crack in the wall through which light might enter. In the high deserts of Chile, in the clear skies above Arizona, on mountaintops scattered across the Earth, and soon in orbit around it, a new generation of telescopes is turning its attention to the darkness between galaxies. They are mapping the universe with unprecedented precision, tracing the subtle clustering of matter, the faint distortions of light as it bends around invisible mass, the rhythmic pattern of baryon acoustic oscillations frozen into the cosmic web like ripples in a pond. And what they are finding is beginning to whisper something unexpected about the vacuum energy, something that may change the conversation entirely. The Dark Energy Spectroscopic Instrument, DESI, is perhaps the most ambitious of these new eyes on the cosmos. Mounted on a telescope at Kitt Peak in Arizona, it peers out through 5,000 robotic fiber optic positioners, each one capable of targeting a different galaxy, capturing its light, splitting that light into a spectrum that reveals how fast the galaxy is moving away from us. Night after night, DESI accumulates data, millions of galaxies, billions of data points, a three-dimensional map of the universe more detailed than anything that has come before. The instrument is designed to measure the expansion history of the cosmos with exquisite precision, to track how dark energy has behaved over the past 11 billion years. If dark energy is truly constant, as Einstein's cosmological constant implies, that behavior should be simple, the same everywhere, the same at all times, a fixed property of empty space that stretches the universe apart at an ever-accelerating rate. But the first results from DESI, released in 2024 after 2 years of observation, suggest something more complicated. The data hint, and at this stage it is only a hint, a statistical tremor not yet definitive, that dark energy may not be constant. It may be changing. The equation of state parameter, a number that describes how the energy density of dark energy relates to its pressure, appears to be evolving with cosmic time. If the cosmological constant were the whole story, this parameter would be exactly -1, unchanging across the history of the universe. But DESI's measurements, combined with other cosmological observations, suggest that dark energy was denser in the past than it is today, that it has been weakening, that something has been slowly changing in the vacuum. This is startling. If confirmed, it would mean that the cosmological constant is not the answer to what dark energy is. It would mean that the vacuum energy, whatever it may be, is not a fixed feature of spacetime but a dynamical entity. Something that evolves, something that perhaps decays. The implications ripple outward like shock waves. If dark energy changes, then the future of the universe changes. The models that predict eventual heat death, an infinitely dilute cosmos stretched into cold oblivion, might need revision. And more urgently for the vacuum catastrophe, if the vacuum energy is dynamical, the puzzle deepens even as it transforms. For decades, physicists have struggled to explain why the cosmological constant is so small. That struggle assumed the vacuum energy was constant, that whatever mechanism cancelled those enormous quantum contributions did so perfectly and permanently. But if dark energy evolves, if the vacuum energy is slowly draining away, then the question becomes not just why is it small, but why is it small now? We might have caught the universe at a special moment in its history, a brief epoch when the vacuum energy happens to be at a value compatible with our existence. This seems to strengthen the anthropic argument, to suggest that we are indeed observing the universe at a time selected by the conditions necessary for observers. But it also opens other possibilities. If dark energy is dynamical, it might be a field, a quintessence to use the technical term, named after the fifth element of ancient philosophy, the substance beyond earth, water, air, and fire that was supposed to fill the heavens. Quintessence models propose a new field pervading the universe, rolling slowly down an energy landscape, its potential energy contributing to the expansion. Such a field might naturally relax to small values over cosmic time, providing a mechanism, however speculative, for the vacuum energy to settle towards zero without fine-tuning. The DESI results are tantalizing, but they are not yet conclusive. The hints of evolving dark energy are at the 2 to 3 sigma level, suggestive but not definitive by the rigorous standards of physics. 2 sigma results are wrong often enough that physicists have learned to be cautious. But the hints are there, the data are real, and they will only improve as DESI continues to operate, as new surveys come online, as the statistics accumulate and the systematic errors are beaten down. We are at a moment of genuine uncertainty, genuine possibility. The vacuum energy may be teaching us something new, even as we struggle to understand its old lessons. And this is how physics often proceeds. Not through sudden revelations, but through the slow accumulation of anomalies, the gradual strengthening of hints until they become inescapable. The history of the vacuum catastrophe itself is a history of accumulating tension. For years, physicists could treat the problem as a curiosity, a technical puzzle to be solved eventually. But as theoretical attempts failed, as the discrepancy remained vast and unmoved by every clever idea, the puzzle became a crisis. Now the observational frontier is adding new complexity. The vacuum is not static, or perhaps it is, and the hints of evolution are statistical flukes. We do not yet know, but we are watching, we are measuring, the universe is speaking and we are straining to hear. What would it mean if dark energy truly evolves? At the very least, it would mean that the vacuum energy problem is even stranger than we thought. A changing dark energy cannot be explained by the cosmological constant alone. It requires new physics, new fields, new dynamics. Some physicists find this exciting. New physics means new opportunities, new phenomena to study, new clues to the deeper structure of reality. Others find it troubling. The proliferation of possibilities makes the problem harder, not easier. If anything can change, if the vacuum is not fixed, then the constraints that might guide us to the correct theory become weaker. The landscape of possibilities expands even as we struggle to navigate it. Perhaps the evolution of dark energy points toward the multiverse. Perhaps the vacuum energy we observe is not the fundamental energy of our vacuum, but the sum of many contributions from different phases, different fields, different aspects of a complex quantum landscape. Perhaps the fact that it is changing reflects transitions between vacuolar, slow tunneling events in which the universe moves from one metastable state to another. This is speculative territory, where theoretical imagination outpaces observational constraint, where ideas multiply faster than they can be tested. But the vacuum catastrophe has always been speculative territory. The problem is so vast, so resistant to conventional approaches, that speculation is sometimes the only tool available. We have followed the story of the vacuum energy from its origins in the paradoxes of classical physics, through the revolutions of quantum mechanics and relativity, into the modern era of precision cosmology. We have seen how the problem crystallized, how it resisted every attack, how it forced physicists to consider ideas that once seemed absurd, and we have arrived at a moment of uncertainty, a moment when new observations are hinting at new possibilities, when the ground is shifting beneath our theoretical feet. But uncertainty is not defeat. It is the natural state of physics at the frontier. Every great discovery was preceded by a period of confusion, of competing ideas, of data that did not quite fit. The history of science is not a march of triumph, but a stumbling exploration, full of wrong turns and dead ends and sudden breakthroughs that came when least expected. The vacuum catastrophe may be solved in the next decade, or it may persist for another century. It may yield to a brilliant insight, or it may dissolve as we learn to ask the question differently. What we know for certain is that the problem has shaped modern physics, has changed how we think about theory and observation, about fundamental constants and the nature of explanation. Consider what we have learned, even in failure. We have learned that the vacuum is not empty. We have learned that quantum fields pervade all of space, that their zero-point fluctuations are real and measurable, that the energy of nothing is not nothing. We have learned that gravity responds to this energy, that the universe expands in ways shaped by the vacuum. We have learned that the cosmological constant is small enough to allow galaxies to form, small enough to allow stars to burn and planets to orbit and life to arise. We have learned that this smallness is not explained by our theories, that it represents the most extreme, fine-tuning problem in the history of science. And we have learned that confronting this problem forces us to consider radical possibilities, multiple universes, anthropic selection, new symmetries, modifications of quantum field theory, changes to our understanding of space and time. The vacuum catastrophe is not just a problem to be solved, it is a teacher, showing us where our understanding breaks down. In the end, what does it mean to understand the universe? For centuries, physics has pursued a vision of explanation in which the laws of nature, once known, would allow us to derive everything. The masses of particles, the strengths of forces, the values of fundamental constants. This vision has been extraordinarily successful. We have unified electricity and magnetism. We have traced the strong and weak nuclear forces to gauge theories. We have mapped the particles of the Standard Model and confirmed their existence in colliders. But the vacuum energy problem suggests that this vision may be incomplete. Some features of the universe may not be derivable from first principles. Some things may be contingent, historical accidents, products of chance, determined by which vacuum we happen to inhabit in a vast landscape of possibilities. This is a philosophical shift as much as a scientific one. It changes what we mean by understanding. If the cosmological constant is anthropically selected, we cannot derive its value from a fundamental equation. We can only explain why values in a certain range are observed, because outside that range, observers would not exist. Some physicists find this deeply unsatisfying. It feels like giving up, like admitting defeat, like abandoning the dream of complete explanation. Others argue that it is simply a recognition of reality, that the universe is under no obligation to satisfy our intellectual preferences. The debate is unresolved. The arguments continue, and the vacuum energy, vast and incomprehensible, cares nothing for our debates. What is clear is that we cannot look away. The problem is too fundamental, too connected to everything else. The vacuum energy touches quantum field theory, general relativity, cosmology, particle physics, the nature of space and time. Any solution would ramify throughout physics, clarifying mysteries we cannot yet name. Any failure to solve it leaves a gap at the heart of our understanding, a lacuna that taunts us with its silence. And so the work continues. Graduate students in universities around the world learn about the cosmological constant problem. They write dissertations on supersymmetry, on string theory, on modified gravity, on quintessence. Senior professors give lectures at conferences, present new calculations, argue over the implications of the latest data. Observers plan new surveys, propose new instruments, compete for telescope time. Theorists fill blackboards with equations, run computer simulations, write papers that few will read and fewer will remember. The enterprise of physics grinds on, driven by curiosity, by ambition, by the stubborn refusal to accept that some questions might not have answers. Perhaps in 50 years, the vacuum catastrophe will be resolved, and future physicists will look back on our confusion with the gentle condescension we reserve for our own predecessors. Perhaps they will have found the symmetry principle that forces the cosmological constant to be exactly zero, or the mechanism by which it relaxes to small values, or the selection effect that explains why we observe what we observe. Perhaps the solution will be obvious in retrospect, one of those discoveries that makes everyone wonder how we could have missed it for so long. Or perhaps the problem will persist, a permanent mystery at the edge of knowledge, a reminder that the universe is not obligated to yield all its secrets. Perhaps there are aspects of reality that are beyond the reach of human understanding, not because we lack intelligence or resources, but because the questions themselves are somehow malformed, because we're asking the wrong thing in the wrong way. This possibility is harder to contemplate, harder to accept. Science is built on the faith that nature is comprehensible, that patient inquiry will eventually be rewarded. But that faith has always been a hope, not a guarantee. The vacuum catastrophe may be testing that hope more severely than any problem before. What we can say, standing here at this moment in history, is that the humming continues. The vacuum persists. The energy density of empty space pushes the universe apart, slowly accelerating the expansion that will eventually isolate every galaxy, every star, every atom in its own shrinking horizon. The same vacuum energy that perplexed the 20th century pioneers of quantum mechanics, that troubled Einstein in his offices in Princeton and Berlin, that has consumed the careers of thousands of physicists in the decades since, remains unexplained. It is the same mystery now as it was then, dressed in more precise data, embedded in more sophisticated mathematics, but fundamentally unchanged. We do not know why the vacuum energy is what it is. We do not know how to calculate it. We do not know if the question has an answer in the form we have posed it, and yet, look at what we have done. We have measured the curvature of space with satellites. We have counted galaxies in billions. We have traced the ripples of the early universe in the cosmic microwave background. We have built machines that smash particles together at nearly the speed of light, recreating conditions that existed a trillionth of a second after the Big Bang. We have developed theories that predict particle masses to 12 decimal places. We have understood supernovae, neutron stars, black holes. We have heard the gravitational waves from colliding remnants, vibrations in the fabric of space-time predicted a century before they were detected. Human beings, fragile and brief, confined to a small planet orbiting an ordinary star, have reached out with their instruments and their mathematics to comprehend the universe on scales unimaginable to our ancestors. If we cannot yet solve the vacuum catastrophe, it is not because we are failures. It is because we are attempting something extraordinary. This is what science is, the slow, uncertain, magnificent struggle to understand. Not a collection of facts, but a process, a way of engaging with the unknown, a willingness to be wrong and confused and frustrated for decades if that is what it takes. The vacuum energy problem is part of that struggle. It is one of the most difficult problems we have ever faced, and facing it, refusing to pretend it does not exist, refusing to give up, is itself a kind of triumph. The night sky is clear, the telescopes point outward, The detectors collect their photons, their gravitons, their cosmic rays. Somewhere, perhaps in a university office or a research institute or the mind of a student not yet born, the insight is forming that will one day unlock this mystery. Or perhaps it is not. Perhaps the solution will come from an unexpected direction, a field we have not yet invented, a question we have not yet learned to ask. The future is open, the problem is vast, the vacuum hums. This is where we leave it, not with an answer but with a question that continues to matter. The cosmological constant problem is the largest discrepancy in the history of science, and it remains unsolved. It is a crack in the foundation of modern physics, a wound that will not heal until we understand something fundamental that we currently do not. It is a humility lesson, a reminder that nature is deeper than our theories, stranger than our imaginations, more patient than our lifetimes. And in that humility there is wonder. The universe keeps secrets. The vacuum holds mysteries. The numbers do not add up, and in their refusal lies an invitation to think harder, to look deeper, to ask what we have been missing. Physicists will accept that invitation, as they have for a century, as they will for as long as curiosity survives. The dark energy pushes, the cosmos expands, the galaxies recede toward the horizon, carrying their light away from us at speeds that will one day exceed the speed of light itself. Not because they move through space faster than photons, but because space itself stretches, carrying them beyond the reach of any signal we might send. 100 billion years from now, if observers still exist, they will see a sky gone dark, a universe reduced to the local group of galaxies bound by gravity. Everything else faded beyond detection. The vacuum will have had its way. The expansion will have won, and whatever the vacuum energy is, whatever secret it holds, it will have shaped that ultimate fate. But that is then. This is now. The telescopes are watching. The equations are being written. The arguments are being had in seminar rooms and coffee shops and the margins of preprints. The vacuum catastrophe endures, but so does the effort to solve it. That effort is part of the human story. Our strange, stubborn insistence on understanding, our refusal to accept mystery as final, our faith that the universe, for all its vastness, is not indifferent to being known. The humming continues, and so do we.